And in this lecture, we will describe mainly three terms: hydrostatic system, thermodynamic equilibrium, and quasi-static process. In the topic hydrostatic system, we will be discussing three more terms related to that as volume expansivity, isothermal bulk modulus, and isothermal compressibility. And connected to your thermodynamic equilibrium, we have mechanical equilibrium, thermal equilibrium, and chemical equilibrium. So we will start with the definition of hydrostatic system. A hydrostatic system is any isotropic system of constant mass and constant composition that exerts on the surroundings a uniform hydrostatic pressure in the absence of gravitational, electric, or magnetic effect. We are familiar with the term hydrostatics. There, you will be discussing pressures or pressure exerted by a hydrostatic system, etc. There, you have the normal expression for the hydrostatic pressure as h rho g. H is the height of liquid column or fluid column above a particular point. So, at that point, the column above that point will be exerting a pressure. In the similar case, here, if we are considering a system and that system consists of a mass, so that system will have a hydrostatic pressure due to its density and the acceleration due to gravity acting there. And there is no other force is acting on that system due to electric or magnetic effect, and also due to the gravitational force by any nearby masses. That is, there is no force are acting on the system. Only the pressure is due to the hydrostatic pressure that we can derive by some methods. So, the hydrostatic pressure only is acting on that. So, such a system is known as a hydrostatic system. And for a hydrostatic system, we are normally defining three quantities like volume expansivity, isothermal bulk modulus of elasticity, and isothermal compressibility. The terms bulk modulus and compressibility are familiar to you, and we can define them one by one. The volume expansivity, which is represented by the letter beta, is defined as 1 by V dou V by dou T at constant pressure. We have the three coordinates: pressure, volume, and temperature. So, volume is changing with respect to temperature. That is a factor known to you when you are heating a body. When temperature increases, volume of that body or that system will also increase. If this is done at a constant pressure, you can write that the rate of change of volume with respect to temperature. That means you are writing as change in volume by change in temperature, which you are writing as dou V by dou T because we are taking it as a constant pressure. And this dou V by dou T depends on the actual volume. Suppose you have a large volume, the increase in volume will be more. And for small volume, increase in volume will be less. So, we will be defining this term volume expansivity for unit volume. That is why you are dividing that term with the volume 1 by V. So beta is expressed as 1 by V dou V by dou T at a constant pressure. This term will be useful in the coming classes. And this term, bulk modulus, is familiar to us. We are normally defining the bulk modulus as volume stress by volume strain. But the modulus of elasticity is simply stress by strain. And the stress you are always written as force per unit area or force by area. Similarly, force by area is pressure. So that is this one. In place of stress, we have dou P. And volume strain you can write as change in volume by original volume. Change in volume is that you can write as say dV. And here we have P, V and T at a constant temperature. You are writing it as dou V. So it is dou V divided by D. And that V goes upwards. That is why you are writing it as V dou P by dou V at a constant temperature. And you are putting a minus sign there. And this minus sign is for making the quantity bulk modulus a positive quantity. Because you know that when you are applying pressure, that means when pressure is positive, you are applying pressure on a particular substance, you can assume it. Suppose you take a rubber ball in your hands and you are pressing it. I think you are familiar with that stress ball that we are using. When you are pressing it, you are applying pressure. Correspondingly, there will be decrease in volume. And always the change in volume you can write as final volume minus initial volume. So when a body is compressed, final volume will be less than initial volume. So final volume minus initial volume will be a negative quantity. So in order to manage that negative quantity, you are putting a minus sign in this expression. So when dV is negative, that negative signs in the numerator and in the denominator cancel. When your pressure is negative, that means the case of expansion of balloon, there the pressure acting on it is negative. That means outside pressure is negative. That is why your system is expanding. There dP is a negative quantity. There you can see that final volume is greater than initial volume in case of expansion. So dV is positive. But dP is negative. Here also the product of this minus and the minus sign that will be resulted due to the minus sign of pressure, they cancel. So that is isothermal bulk modulus of elasticity. And this term isothermal, that is common to you, which is at a constant temperature. That is a meaning. Iso means constant. And this term is also familiar as you are defining compressibility as the reciprocal of bulk modulus. So this K is 1 by B. This is not K, it is kappa, the Greek letter kappa. Kappa equal to 1 by V, that you can write as minus 1 by V dou V by dou P at a constant temperature. So we have the three terms: isothermal compressibility, isothermal bulk modulus of elasticity, and volume expansivity. Now, a term common to you, thermodynamic equilibrium. In mechanics, you will be saying that equilibrium means the resultant force acting at a particular point is zero. Here also, a system which is at rest, that is the meaning of that, we can define the thermodynamic equilibrium as a system which is in mechanical, thermal and chemical equilibria is said to be in thermodynamic equilibrium. That means if a system is in mechanical equilibrium, chemical equilibrium and thermal equilibrium, then that system will be in thermodynamic equilibrium. So, in order to satisfy the condition of thermodynamic equilibrium, a system should be in all these three equilibria conditions: mechanical, thermal and chemical. If any of these three, that means mechanical or thermal or chemical, whatever, it is not satisfied, you can't say that your system is in thermodynamic equilibrium. And now we can define this mechanical, thermal and chemical one by one. First we will look for mechanical equilibrium. A system is said to be in mechanical equilibrium if there is no unbalanced forces acting on any part of the system or on the system as a whole. If there is an unbalanced force acting on a system, that means if some gas is contained in a vessel with a possibility of expanding sides, if unbalanced force is acting, that side will be moving. That means your volume will not be constant, or there will be some resultant forces acting on the system. Thermal equilibrium means a system is said to be in thermal equilibrium if there is no temperature difference between the different parts of the system or between the system and the surroundings. That is clear? Whole part of the system should be at the same temperature, and also the temperature of system and the surroundings should be same. At that condition, you can say that it is in thermal equilibrium. And in chemical equilibrium, a system is said to be in chemical equilibrium if there is no chemical reactions within the system and no motion of any chemical constituent from one part of the system to another part. So, no chemical reaction as well as there is no movement of particles within the system. If these three conditions are satisfied, you can say that your system is at thermodynamic equilibrium. And now what happens if an unbalanced force is allowed to act on the system? That we can look. If an unbalanced force is allowed to act on the system, then the thermodynamic equilibrium is disturbed and the following situations may arise. So, when an unbalanced force, you can just think of a pond which is calm, and you can see that when you are putting a stone on the surface of that pond, what happens? A small disturbance will be occurring at the surface. That means you can see that some waves are produced, or you can see that it is a turbulence. In Malayalam, you will consider it as a churi, that is a turbulence. So, a wave is produced. That means your system will disturb. In a similar manner, if an unbalanced force is at, what happens? We will be considering three cases. The first one, the system as a whole may execute some sort of accelerated motion. The unbalanced force may produce turbulence, waves, etc. So, there can be a motion of the system, and this unbalanced force may produce turbulence, waves, etc. As a result of this turbulence, acceleration, etc., a non-uniform temperature distribution may occur. So, in the initial condition, we have mentioned that if there is an unbalanced force, it is producing waves, etc. So, as a result of this, what happens? There will be a temperature difference. So when there is unbalanced force, your mechanical equilibrium is lost. And when there is a temperature distribution, that means temperature difference inside the system, so thermal equilibrium is also lost. And the sudden change in the forces and in the temperature may produce a chemical reaction of the motion of chemical constituent. That means it is disturbing your chemical equilibrium condition. So when an unbalanced force is acting on the system, chemical, thermal and the mechanical, three equilibrium conditions are disturbed or they are not satisfied. And our last term, quasi-static process. We have mentioned about a thermodynamic process. In a thermodynamic process, there will be change in thermodynamic coordinates. That is thermodynamic process. So, a special type of thermodynamic process is known as quasi-static process. The term quasi means semi. Static, as you know, it is stationary. So, semi-stationary means it is almost at equilibrium. Only slight variation or an infinitesimally small variation from the equilibrium condition. So, a quasi-static process refers to an idealized process where the change in state is made infinitesimally slowly so that at each instant the system can be assumed to be at a thermodynamic equilibrium. So actually we know that when there are slight variations from the equilibrium conditions, you can say that your system is not at a thermodynamic equilibrium. But if the variation in the temperature, their pressure, etc., they are very, very small, or if they are taking place very slowly, you can say that your system is almost at a state of thermodynamic equilibrium. So, such a process in which the system is an idealized process or an idealized slow process in which always your system is nearer to thermodynamic equilibrium. Such a process is known as a quasi-static process. And that's all.